Okay, today was a day where it's very easy to just memorize the rules for horizontal asymptotes without actually understanding what's going on. So I hope that we can understand conceptually the three different cases, which I've laid out here. There's three different functions here. We have one where we have a higher degree on bottom than on top, 3 on top compared to 4 on bottom, and then a higher degree on top compared to a lower degree on bottom, 5 to 2, and then one where the degree on top and bottom is the same, and these lead to three different cases graphically. So what we need to think about is what happens when we plug in infinity for x, and this is why this is kind of tough to understand because we can't really conceptualize infinity, we can't fathom it. But basically infinity is so big that when you plug in infinity to x, you get infinity cubed. That's so much larger than the rest of the numerator that this ends up just kind of not mattering. 3x squared minus 7 when you plug in infinity is basically nothing compared to infinity cubed. And then same thing on the bottom. Infinity to the fourth is so large that basically 2x cubed plus x minus 2 doesn't even matter anymore, because they're so small comparatively. Now they matter a little bit, enough to make a small change, which is why we're approaching an asymptote instead of actually touching it, but basically they're not even there at infinity. So same thing down here, everything except for the variable with the degree, the variable with the highest exponent, basically end up going away. And same thing down here, so we're just looking for that biggest exponent. So at infinity, these different functions are just going to approach these other functions with the term that only has the highest degree in the numerator, or the highest exponent in the numerator and denominator. So what we end up getting here now is we have to think about what's happening at infinity here. Well, in this case, and we can write this as, sorry, let's do black. We can write this as, so we have x cubed over x to the fourth, that's going to cancel to 1 over x, right? Which we know has an HA, a horizontal asymptote at y equals 0, right? So basically what we end up saying is if the degree is bigger on bottom than it is on top, well, the bottom is going to become so big, so freaking big, that the top is going to be very small in comparison, which means that the output is going to approach 0. If you do something small divided by something, or relatively small divided by something really big, you're going to approach an output of 0. So down here, we could cancel this and say that this is going to approach an x cubed like function. So we say there's no horizontal asymptote because x cubed does not have horizontal asymptotes, right? So what's going to happen is this is a rational function, but at infinity it's going to approach a cubic function, because at infinity, when we cancel this out, that's what we're left with, x to the fifth over x squared. So when the degree is bigger on top, there's no horizontal asymptote. Now, the tie is a little bit more interesting, because what we end up getting here is the x cubes cancel out, and we just get 3/5. So again, only at infinity, that's all we're worried about when we talk about these rational functions, horizontal asymptotes. At infinity, this function is going to approach an output of 3/5, because again, the rest of the function is not really going to matter. The x cubes are going to cancel each other out because infinity cubed over infinity cubed is the same thing, so those cancel. All that's left is 3/5. So whatever this fraction is, whatever these coefficients are, that's going to determine the horizontal asymptote when the degrees match, when the degrees are the same on top and bottom. So in this case we say y equals 3/5 is the horizontal asymptote. Okay, so there's a lot of examples of these on the problem set, and you can also review the day 5 lesson for more examples. And you really just want to go back through this and make sure you understand the three different cases conceptually, so you do not have to memorize, because this will continue to show up through calculus.